All right. So the day before yesterday, we learned how to differentiate sine functions and cosine functions, and we continued to work with that yesterday as well. Tomorrow in seminar, I'm going to give you a quiz, so it'll be a 25-minute quiz because that's how long the seminar is. If you want to start the quiz 10 minutes early at 8:35 tomorrow, you can certainly do that. But my idea for the quiz tomorrow is that it would contain, well, very basic kind of, I mean, not so basic that I'm going to just throw the marks at you, but basic in terms of some basic rules. So, I look at something like this. I'm not picking this for any particular reason. It just happened to be where my sight landed when I turned around. That, I think, is a fairly standard kind of question that I would expect you to be able to differentiate on the quiz. I wouldn't, we had a lot of discussion yesterday about one or two of these problems where it was like chain rule within chain rule within chain rule. The purpose of the quiz is not to test your ability to do that kind of thing. So if I were to just go through here and circle these, I almost think C is too easy, but it's fair game. Same with B. Something like this, as opposed to something like this. Now I realize that this one is really simple. This one is going to involve the quotient rule. But the point I want to make is you should definitely know the difference between differentiating something like this, and Arden, the discussion we had this morning about logarithms and brackets is the same kind of thing we have here, right? We know that squared goes with the x. Differentiating something like that and differentiating something like this, of course, are two entirely different things. Because this, and if you listen to the words carefully, it should make sense. On the right-hand side, what we have is a trigonometric function of a power. And on the left-hand side, we have a power of a trigonometric function. So when you differentiate the expression on the left, this is y equals cosine of x quantity squared. Sorry, I got my screens mixed up. Give me a second. There we go. Demi and Nicole, can you give me a thumbs up if you can see my screen and me writing? Okay, good. Thank you. So sorry about that, everyone. So when we differentiate the equation on the left, or the function on the left, we apply the power rule, and we're going to have dy dx equals, the power rule says you wrap the 2 around the base, which stays the same. You drop 1 from the exponent and multiply by the derivative of what's inside. So that's the derivative of cos squared of x, as opposed to the derivative of this would be negative sine of x squared. I'm just going to throw those brackets in there for good measure, times 2x. So there's a big difference there. One, you start off with the power rule because predominantly that's what it is. The one on the left is a power. The one on the right contains a power, but it's not a power in its entirety. What it is a trigonometric function of a power. So your quiz tomorrow in the seminar will contain, questions like this, things probably that would involve quotient rule, power rule, your rules, of course, for sine and cosine, as well as I don't have 4 up here for some reason. As well as, I got it down here maybe, no, implicit differentiation. Not sure why I don't have it, but I'll have to pull it up. So let me grab that implicit differentiation work and show you what I'm referring to. What do we got here? Page 314. I just copied the wrong question. Page 314, number 2. That would be on the quiz as well. So I envision here, I haven't typed up the quiz yet, it won't take me long, but I envision 4 questions kind of thing. 4 functions, what's the derivative of each one? Simplify if at all possible. So all that being said, does anybody have any questions? From number 2 on page 314, which was the new extra set that I assigned. Marcel? 2E. Okay, let me grab this entire thing and then we'll get going on it. So we're using implicit differentiation. And we have sine x cos y plus cos x sine y equals 1. And this qualifies as a perfect example of what I would put on the quiz tomorrow in terms of implicit differentiation. By the way, we're going to have to use the product rule for each of these 2 terms. The first term is sine of x times cosine of y. So we need to think of this as a product of 2 things. So the product rule applied to that will be the derivative of the first. The first is sine. The derivative of sine is cos, times the second, which is cosine of y, plus the first, which is sine of x. And now things get a little bit trickier, times the derivative of the second. So what is the derivative of the cosine of y? The derivative of the cosine of a thing is negative of the sine of the thing times the derivative of the thing. You know, if it were just sine of x, pardon me, if it were just cosine of x, we would just write negative sine of x. But because it's not cosine of x, it's cosine of a function of x, we have to multiply by the derivative of that. You can think of that as being the implicit rule differentiation, the implicit differentiation rule. You can think of it as the chain rule. It doesn't really matter. Continuing on with the second term, the derivative of the first, well, the first is cosine of x, so the derivative is negative sine of x, times the second, which is sine of y, plus the first, which is cosine of x, and then we're going to have to multiply by the derivative of the second. And because my train of thought got interrupted by that, I'm going to double check this in a second. But the derivative of the second would be cosine of y, and then dy dx. So I'm going to go from the beginning, and by the way, this is equal to 0. So I'm looking up here, running all of this through my head to get to the next line. The derivative of the first is cos x times the second is cos y, plus the first, which is, where am I? Wait a minute. Plus the first, which is sine x, times the derivative of the second, which is negative sine y dy dx. Now I'm moving on to this one. The derivative of cos is negative sine times the second, plus the first, which is cos, times the derivative of the second, which would give you cos y dy dx equals 0. Are you fine with that, Marcel? It's equal to 0 because the derivative of 0 is, the derivative of 1 is 0. Is that where? Okay, but we'll finish it anyway. The same thing goes, and those of you that are taking Math 30-1 with me right now, this is very similar. Who am I talking to here? This is very similar to taking all of your terms that have x in them when you solve a logarithmic equation and moving those terms with x to one side. But here we want to solve for dy dx, so we're going to move all of the terms that involve dy dx to one side. It really doesn't matter. I'm going to leave the dy dx terms here. So I have cos x, cos y, dy dx, and then I have minus this term of sine x, sine y, dy dx. and it's equal to, I have to move this term over, sine x sine y, wow, minus cos x cos y Is that right? Wow, how many of you see what's going to happen here very shortly? This is pretty amazing, and I will have to give some thought as to why this is going to happen. When I factor the dy dx out, I'm going to have cos x cos y. There should be a little s in here. Sorry about that. Minus sine x sine y. This is equal to sine x sine y minus cos x cos y. Still with me, Marcel? When we divide, we're going to have dy dx equals the right-hand side, sine x sine y, minus cos x cos y, over cos x cos y minus sine x sine y, and this is equal to -1. There's a couple of ways to know that it's equal to -1. One is just to know the rule that binomials that are negatives of each other have this form. The other thing that you could do is you could factor a negative out of the top and turn the top into the bottom. What this tells me, I got to give some thought to this, is that if you could graph this relation that is in E, it would be a straight line with a slope of 1, because the derivative is 1 everywhere. Which is very bizarre, and I'm not going to go to my computer to graph it. We can't graph this on a graphing calculator, first of all. And is that the answer, -1? Okay. We can't graph this on a graphing calculator because you have to be able to rearrange for y. I can graph it in my graphing program, but I have to type in the relation, and I can't do it from here very easily. Later on in the class I will do so. I'm having a hard time. I mean, it's got to be a straight line with a slope of 1. It has to be. There might be holes in it because of maybe non-permissible values. I don't think there are, but with relations like this, there could be. But we can check it out later. Anyway, I want to move on. Any other questions from number 2, which is what I'm primarily worried about here? Farhan? B? Mm-hmm. So x cos y equals sine of x plus y. So when I differentiate the left-hand side here, Farhan, I'm going to have to use the product rule because I have x multiplied by something. The derivative of x is 1 multiplied by the second, which is cosine of y, plus the first, which is x, multiplied by the derivative of the second, which is negative sine of y, times dy dx. I think that set of brackets is really important. Whether you end the brackets after sine y or end the brackets after dy dx doesn't matter, but I think you need to separate that negative sign of y from the x. Otherwise, you might be rooked into thinking it's x minus sine y. So just be cautious about that. Equals. Now, on the left-hand side, we had a product of some things. On the right-hand side, we do have a sum, but it is not a sum in totality. What it is in totality is a sine. So the derivative of that will be cosine of x plus y multiplied by the derivative of x plus y, which is a sum whose derivative is going to be the derivative of x plus the derivative of y. Now, again, I'm going to address the 3 or 4 people in the room who are in my 30-1 class right now. This is very similar to the logarithmic equations we were doing this morning, where we had x inside of the brackets with a binomial, and we had to multiply that logarithm through to get the x out in the open. We have to do that here. So on the left-hand side, I have cosine y, and then I have minus x sine y dy dx. And on the right-hand side, I need to multiply this by the 1 and by the dy dx. So I'm going to have cosine of x plus y, and then plus cosine of x plus y dy dx. And now I can identify the terms that I need to move to one side, so that I can factor out the dy dx, so I could then solve for dy dx. So these are the two terms that need to go together on one side. I would probably move them to the right side. So I have cos of x plus y multiplied by dy dx, and then plus x times sine y multiplied by dy dx. This is equal to cosine of y minus cosine of x plus y. So Farhan, are you okay with those, I guess, 3 steps? Okay. We're really just about done, and unlike the previous question that Marcel had asked about, I don't think this is going to simplify to anything amazing. We're going to factor the dy dx out of the right-hand side and have left cosine of x plus y plus x, plus x sine y. And this is equal to cosine of y minus cosine of x plus y. I don't know why I believe this, but it troubles me that there's an x on one side of the equation and not an x on the other. That could just be the way it is, but for that reason I want to. So there's this x right here. I feel as though there should be an x over here someplace, but maybe I'm wrong. I want to check though. I'm wrong. There is no x there. So now all that remains here, Farhan, is to divide the left-hand side, which is cosine of y minus cosine of x plus y, over what dy dx is being multiplied by on the right-hand side, which would be cosine of x plus y plus x sine y. We're okay with that? Okay. We're going to move on now. Yeah.
For E, is that an identity by any chance?
No. Well, no. No, it isn't. You're thinking maybe a double angle identity of some sort? No, because there's x's in one and y's in the other.
I did it with the sum and difference identity.
Oh, you are right. It's not a double angle identity. Thank you, Makai. It's a sum and difference identity. I wish I would have seen that, because it certainly makes your job easier, doesn't it? Sine of x plus y, when you go to your identity sheet, is sine of x cos of y plus cos of x sine of y. And you know, you shouldn't, I'm not going to feel bad, and you certainly shouldn't feel bad for not catching that. There's a lot of things to keep track of. So it turns out it wasn't a double angle identity, but there is an identity we could use here. This is not question E. All I'm saying is part of question E is in this identity, so you can rewrite this as sine of x plus y equals 1, and differentiate it using the derivative of sine times the derivative of what's inside. And then rearrange for dy dx. Yeah.
I think it's a bad move to do the same thing for B. Use the same identity.
So, Evan, are you asking in question B, would it be a bad move to change this to sine x cos y? I think it would be, because sine of x plus y, the thing I've circled, is simpler to differentiate rather than the other thing that it's equal to. So the best way to think of it is, I think it would be a bad move to change this. It was a bad move on my part not to change this to that to make my life easier. You know, but you're also starting to gain more experience at this level in math, everybody, where, you know, is something a good move always or a bad move always? Sometimes it is and sometimes it isn't. You have to kind of play it out. I think it would be in this case only because I don't see anything over here that would maybe combine with those other things. You know, the left-hand side in B is just x cos y. It's not even sine x cos y. If it were this, then I think it would be a good move to change the thing that's circled to this, because then you could subtract sine x cos y from both sides and have something much simpler to deal with. Okay, we are going to move on. And we're going to just spend one more day. I contemplated not doing this lesson to pick up an extra day, but I think this is just as valuable as differentiating sines and cosines. Tomorrow, as I said in the seminar, we'll write the quiz. In our regular class, we are just going to be looking at derivatives of, well, everything else that's trigonometric. Tangent, cotangent, secant, cosecant. So we're going to be learning those. Nicole, Demi, and Zach, I instructed Ms. Townsend to give you a handout for today's class, but if she did give you that handout, we're not using it today. That's going to be for tomorrow. So we don't need it today. We'll take a look at it tomorrow. So we're going to be looking at graphical properties of sine and cosine functions using differentiation. So for example, if we know how to differentiate sine functions and we know how to differentiate cosine functions, then you ought to be able to find the equation of a tangent line to a sine or a cosine function. Don't forget, the equation of a tangent line can be found using your point-slope formula, where your primary focus becomes what is the slope and what are the coordinates of a point on the graph. So as we go through today's lesson, it's probably a good idea to have your trigonometry formula sheet in front of you, not necessarily because we're going to use identities, but because we're going to be referring to the unit circle. So first of all, it doesn't matter what this function looks like. The slope will be the derivative of the function at the x coordinate. So the only thing that's different here is it's trigonometric in nature. The x-coordinate is pi over 6. The y-coordinate will be f of pi over 6. And I want everybody to think very carefully about the difference between what I'm highlighting in blue and what I'm highlighting in yellow, because they are different things. What I'm highlighting in yellow is the value of the derivative of the function when x is pi over 6. That gives you the slope. What I've highlighted in blue is the value of the function when x is pi over 6. That gives you y. So let's find the y-coordinate first, then we can do the calculus. The y-coordinate will be f of pi over 6. which will be sine of, pardon me, which will be cosine of pi over 6 divided by sine of 2 times pi over 6. That means that f at pi over 6 radians is equal to cosine of pi over 6 over sine of pi over 3. Because 2 over 6 reduces to 1 over 3. Right, this 2 divided by that 6 gives you 1. I'm not going to put the 1 in. Gives you 1 divided by 3. So let me rewrite this someplace. I don't think most of us need to rewrite it, but I want to really, I don't want to lose anybody here. So we have the y coordinate equals cosine of pi over 6 over sine of pi over 3. This is the y coordinate. This is y1. Did I write y2 over here? No, I wrote y1. Good. So I just want to remind you that using the unit circle as a tool, cosine of pi over 6 will be the x coordinate at pi over 6. Sine of pi over 3 will be the y coordinate at pi over 3. So you have the unit circle in front of you, but you may not be allowed it next year. When I take a look at quadrant 1, which is where pi over 3 and pi over 6 are, remembering that the unit circle intersects the x and y axes at 1 in quadrant 1, pi over 3 is here, roughly. Pi over 6 is here. I mean, I don't look at the unit circle, and many of you don't as well. Just looking at this, boy, is that ever a wobbly line. I can see that that x coordinate is half of that distance of the circle. I know that that has an x coordinate of 1/2, and hopefully you've memorized that if it's 1/2, the other one is root 3 over 2. On the other hand, this has a y coordinate of 1/2, so this point here at pi over 6 is root 3 over 2, comma 1/2. I realize I'm giving you the unit circle. You don't have to go through this process. But I think there's something to be learned there. So what is the x coordinate at pi over 6? I'm just going to go back to here because I know what they are. The x coordinate at pi over 6 is root 3 over 2. The y coordinate at pi over 3, oh, well, the sun has come out here, hasn't it? Because the y coordinate at pi over 3 is also root 3 over 2, is it not? Well, that was enlightening. The slope of the tangent, or the y coordinate rather, is 1. So the point is pi over 6 comma 1, and now we have to work on the derivative so we can find the slope at that point. I'm going to pause there. Any questions with the work on finding the y coordinate? Looks like you have lots of workspace left. I'm going to go to a new page. I need you to confirm to me that it was cosine of x over sine of 2x. Okay. Is there a smart way we can go about this? Well, let me show you, and you might want to not write this down. Okay? Or you can write it down, I don't care. But I'm going to do it if you don't see the smart way, and then I'm going to do it using kind of a shortcut. If I use the quotient rule, I have dy dx equals the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. And I admit that my brain is on autopilot right now. I don't mean to rush through it. Now I'm going to explain all the steps as I double check my work. The top is cosine of x, so the derivative of cosine of x gives me the negative sine x. So this is the derivative of the top times the bottom. Then the quotient rule says minus the top. The derivative of the bottom, well, the bottom is sine of 2x. The derivative of sine is cosine of the same argument times the derivative of the argument, and then it's over the bottom squared. Even though there's a simpler way to go about this, you should be able to follow that, I hope. Now, listen very carefully. I'm going to give you the same advice here that I gave you every time we found slopes. Don't simplify this. It doesn't matter because we're going to eventually put pi over 6 in for x. So if you spend a whole bunch of your valuable time simplifying it, one, you've lost time, and two, you run the risk of making a mistake. Now, some of you might prefer to simplify it, but I would just put pi over 6 in here. So this is negative, well, I'll write it out. Negative sine of pi over 6 times sine of I am just going to say to you that I'm not going to write 2 times pi over 6 every time there's a 2x. If x is pi over 6, 2 times pi over 6 is pi over 3. And then minus cosine of x. And then cosine of pi over 3, because that's 2x times 2 over sine of pi over 3, because it's 2x quantity squared. I'll double check all of that. You double check it as well. Give me a nod or a thumbs up if you feel that you're in agreement. Tyson, you're nodding. Evan. Okay, Zach's got it. I think that's enough to confirm. I mean, one of the reasons I'm asking you to check is for you to think about the math, but also I want you to check my work, okay? So now, what do? We go to our unit circle. Sine of pi over 6. Sine of pi over 6 is 1/2, and you're going to have to correct me if I'm wrong, but I'm just picturing the unit circle in my head. The y coordinate at pi over 6 is 1/2. So I have negative 1/2 times the y coordinate at pi over 3. Sine at pi over 3 is root 3/2, minus cosine at pi over 6 is root 3/2. Cosine at pi over 3 is 1/2, and I need to multiply by 2. This is over. Sine at pi over 3 is root 3/2, and I need to square it. I'm going to take a minute here and see if my trigonometric values are correct. And again, you're not plugging anything into your calculator necessarily to check these, but I'm asking you to confirm that, where I put sine of pi over 3 is root 3/2, that is in fact what sine of pi over 3 is equal to. That 2 at the very end of the top looks like it might be a squared, but it's not. It's times 2/1. Not really getting any confirmation yet. I am now. Okay. So I'm going to do something here. I'm not going to cancel those two 2's. I'm just going to leave them. Okay. And the reason I'm not going to is because on the top we have negative root 3/4 minus 2 root 3/4. 2 times 1 times root 3/2 times 2. And on the bottom I have 3/4. When I square root 3, I get 3. When I square 2, I get 4. So I've just looked ahead and said, well, it's all over 4, so why don't I just multiply the top and the bottom by 4, and I get a slope. All the 4's cancel. I get a slope of negative root 3 minus 2 root 3 all over 3, which is negative 3 root 3 over 3, which is negative root 3. I have negative 1 root 3 minus another 2 root 3. That's where I'm getting negative 3 root 3. So the 3's cancel, the slope is root 3. I'm going to put that in my list here for the slope. It's negative root 3. And now I'm going to show you the simpler way we could have done it. The simpler way we could have done it is to take that function y equals cos x over sine 2x and said that's y equals cos x over 2 sine x cos x. Now the double angle identity has a purpose. And this is what I've tried to teach you whenever we learned about identities in Math 30. You use an identity if it's going to take you somewhere. You don't automatically say, oh, I could use an identity here, I'd better do it. This takes us someplace because these two cosine functions cancel. And I'm left with y equals 1 over 2 sine x, which can be written as 1/2 sine of x to the negative 1. And I'm going to digress, or take a detour here, because it's important to know, but it's not necessary for this question. You know how we put exponents right next to the sine or right next to the cosine? You don't want to do it when the exponent is negative 1. Because if I write that as sine to the negative 1 of x, that has a special meaning. It's the inverse sine. Right? That sine to the negative 1 on your second sine function on your calculator does not mean an exponent. So I would avoid that. Okay, what happens if you differentiate this? This is a piece of cake. dy dx equals negative 1/2 sine of x to the negative 2 times the derivative of sine of x, which is cos of x. This derivative is cos of x over 2 sine squared of x. X is pi over 3. No, x is pi over 6. So let's put pi over 6 in there. I'll have cosine of pi over 6 over 2 times sine of pi over 6 squared. Cosine of pi over 6 is root 3 over 2. Why am I not getting a negative? Because I forgot to put my negative, didn't I? I know it's going to be negative because we already did this. So cosine of pi over 6 is root 3 over 2 over negative 2. Sine of pi over 6 is 1/2, and we need to square that. So I end up with root 3 over 2 over negative 2 times 1/4. Negative 2 times 1/4 is negative 1/2. Multiply top and the bottom by 2. You'll get root 3 over negative 1, which is negative root 3. I don't want to bamboozle you into believing that the simpler way involves no work. You still have to understand how to determine these trig ratios. Anyway, now that you have the slope and the point, you're going to put the slope and the point into y minus y1. So that will be y minus 1. y1 is 1. Equals the slope, negative root 3. The slope is negative root 3 times x minus x1, which is pi over 6. And everybody, aside from a little bit of algebra here, we're basically done. Let's multiply that negative root 3 through to get y minus 1 equals negative root 3x plus pi root 3 over 6. It's not a huge deal, but when we write an equation equal to 0, which is what we do in this course for a linear equation, we don't want fractions. We don't want over 6. So I'm going to multiply everything by 6 to get 6y minus 6 equals negative 6 root 3x plus pi root 3. The only thing the 6 cancels with is the last term of pi root 3 over 6. And then we can move everything to the left side and get the following. 6 root 3x plus 6y plus pi root 3 minus 6. Go ahead, Ben. Definitely. Minus pi root 3 plus 6 root 3x. Yeah. So, we're really getting deep into territory here where I want to be careful to make sure that you understand what's expected on an exam, because some of the stuff we learn is not. This is expected on an exam, but maybe not to the extent of the amount of work involved. For example, maybe instead of cos x over sine 2x, it was just cos x over sine x. Or maybe it was just sine x. What's the equation of the tangent? So we have one more example to do, but I've changed the example. So what we want to do here is, for this trigonometric function, we want to find out where all the max mins are from 0 to 2 pi. And we're not going to be doing a lot of detailed analysis with trig functions and graphs, but why don't we graph this to see what this thing looks like, so at least we know what to expect out of our work. I have cosine of x and then plus sine of x quantity squared. And again, Arden, it seems we were having this discussion as well with logarithms. I know that when you type sine bracket x n bracket squared, to me it looks like that squared is only being applied to the x, to me. But it is in fact squaring the whole sine. Okay. Let's make sure our calculator is in radian mode. And we're going to go zoom trig, which is zoom 7. And then we're going to remember that when you go zoom trig, when you do a zoom trig, your calculator essentially goes from negative 2 pi radians to 2 pi radians. And I think it goes from negative 4 to 4. So we are asked about this function from 0 to 2 pi, so we're going to manually go in and change the window settings to start at x equals 0 and go only up to 2 pi. I'm also at the same time going to only go from negative 2 to 2 for y, because there's a lot of space up here that I don't need, and a lot of space down here I don't need, and I don't want this at all. So what I'm doing is basically setting my window settings up so it will be that. Yep.
I was just wondering, would that be considered even symmetry then?
This is even symmetry, yeah. Which tells you that if you were to put negative x in, you'd get the same function. And this brings up a point from yesterday. I don't know if you remember, but at the end of yesterday's class, we were able to take the negative out of a sign and put it in front. And I had shown everybody that I think it was sine of negative 4x, but it was just written as negative sine of 4x, or maybe there was another negative in front. It doesn't matter. And I said that's a negative angle identity for sine. Well, the negative angle identity for, so it's this. Sine of negative x is the same as negative sine of positive x, turns out. For cosine, cosine of negative x is the same as cosine of x. It's a very useful thing to keep in mind, because anytime you're taking the cosine of a negative quantity, throw it out. The reason for that, and we're getting a little off topic, but I don't feel I can just say that and not address it, is cosine is the x coordinate on the unit circle, right? So think about having a rotation angle. I guess I'll need a circle. So we have a circle. It's the unit circle, although it doesn't matter. Here are our axes. And I am going to take the initial arm and rotate it positive theta. That's theta. The cosine of that is whatever this x coordinate is, right? Now, if I take the same initial arm and I rotate it the same amount in a negative direction, it's going to intersect the circle in such a way that the x coordinates will be the same, because those two angles are the same, right? One is positive theta, one is negative theta. So cosine of theta, this is cosine of theta, the x coordinate for theta, and cosine of negative theta, this is negative theta. They have the same value. Okay, anyway. Let's adjust our window settings here. I said I'm going to go from 0 to 2 pi, so I hit the window setting and I'm just going to start at 0. And I said, let's go from negative 2 to 2. So now I can graph. We should have a max here, a min here, a max here. I know you can't really tell, but this will be a minimum. It's at the very bottom of the graph, and this will be a minimum as well. Okay. So our goal here is to learn how to connect the first derivative of the function, which is related to increasing and decreasing, to this graph. So it is y equals cosine of x plus sine squared of x. Am I correct in my memory there? Okay, let's differentiate it. Max mins are related to the first derivative in the first derivative chart. Derivative of cosine is negative sine. The derivative of sine of x quantity squared is 2 times sine of x to the 1 times cos of x. I'm using the power rule. I'm wrapping the 2 around the sine of x, which stays the same. I'm dropping 1 from the exponent, and then I'm multiplying by the derivative of sine of x. Okay, all right. Well, let me just clean it up. I don't think we really need to rewrite this to see what's going to happen and to proceed, but I'm going to write it without the brackets and without the exponents. Some of you might immediately zero in on the 2 sine x cos x, thinking double angle identity. It's a waste of your time. Because really what we want to do is we want this to be in factored form so we can identify the critical values of x. And I can factor out, I'm going to go ahead and factor out a negative sine of x. And I will have left 1 plus 2 cos of x. No, 1 minus 2 cos of x. And that means each of those factors can be set equal to 0. Now, okay, there's a lot going on here. Another thing I have to tell you is, you know how this equals 0 bit of business I've said to you, don't do that? Do it for trig, okay? It's hard to imagine without that equals 0 what's going on. So that means our derivative, this is still our derivative, dy dx equals that. We'll have critical numbers wherever negative sine of x equals 0 and wherever 1 minus 2 cos x equals 0. Well, I can multiply both sides of this little equation by negative 1 and still get sine of x equals 0. Don't, everybody, don't do that here. Don't get rid of that negative in front of the sign, because if you do, it's no longer the derivative. That's the risk you run of putting equals 0, is you can mathematically get rid of things, but you shouldn't. Here, this becomes 1 equals 2 cos x. So 1/2 equals cos x. Don't forget, cosine is the x coordinate on the unit circle. Sine is the y coordinate. Now, you know, I made this as simple as I can, believe it or not. We're only going from 0 to 2 pi. Right? Do I include 0? Well, let's take a look. I include 0 and I include 2 pi. So on the unit circle, I'm going to go ahead and use this one. On the unit circle, sine is 0 at this location and this location. That's for the sine x equals 0. You don't need to write all this down. I'm just in instruction mode here. We also had cosine of x equals 1/2. Cosine is the x coordinate. X is 1/2 here. So we're talking about this point and this point. So I'm going to start at 0 and write down all of our critical values of x. We have a critical value of x of 0 radians. We have a critical value of x of pi over 3 radians. We have a critical value of x of pi radians. And we have a critical value of x of 5 pi over 3. I'm pretty sure those numbers are right, but looking at your unit circle, can you confirm them? Okay. So think about this, and you have to think about this a little bit differently than we would normally do. This is an interval. This is an interval. This is an interval. And this is an interval in our first derivative chart. We have to go from 0 to pi over 3, from pi over 3 to pi, from pi to 5 pi over 3, and 5 pi over 3, finally to 2 pi. Ben?
Would 2 pi be considered a critical value?
Are you saying we need this? Okay. Yes, we do. We do for a couple of reasons, and you're going to see why it doesn't really matter. We do have to end at 2 pi because that's where the interval ends. But you're right, it is critical. It's critical because that's where the interval ends. It's where the function ends. And it's also critical because sine of x is equal to 0 when x is 2 pi. You're right. That's the weird thing about circular functions, right? We're back in the same place. The beginning and the end are the same place. So, what's our chart look like? We are going to go from negative infinity. Nope. We are going to go from 0 to pi over 3 radians. We have to go from pi over 3 radians to pi radians. We have to go from pi radians to 5 pi over 3 radians. We have to go from 5 pi over 3 radians to 2 pi. And across the top, we are going to put all of the factors of our derivative. This is the same thing we did with non-trigonometric derivatives. Are you sure, Liam? Okay. Across the top, I'm going to put negative sine of x. And I'm going to put 1 minus 2 cos of x. Is that right? Okay. What's different here is you don't have that negative turning into positive rule. It just doesn't work because it's trigonometric. So if you can wrap your head around a different way to do this, then that's fine. But ultimately, what you need to do is calculate what negative sine of x is in this region. Now, personally, I know, and I'll show it to the camera so that Buck, you three can see what I'm talking about. I know from 0 to pi over 3. Here's 0, here's pi over 3. I know that from 0 to pi over 3, the y-coordinate is positive everywhere in that region. So any place between 0 and pi over 3, sine of that angle is positive, so negative sine is negative. I know that. And in fact, I know that that's the case in the next interval as well, because, don't forget, this is x and this is y. Here's the first interval. Everywhere in here, the y-coordinate is positive, so sine is positive, which means negative sine is negative. Everywhere in here, it's true as well. The y-coordinate is positive everywhere there, so sine of the rotation angle x is positive. Negative sine of x will be negative. As soon as I dip below in this region or this region, sine of x is negative, so negative sine of x is positive. But what I'm saying is I know from experience that some students need to take their calculator and go negative sine in radian mode and pick a number that's between 0 and pi over 3, like 0.2. I can't really, right now, wrap my head around whether this is positive or negative in the same way. I can kind of show you what my thinking is. In this first region, cosine is a positive number. I'm going to think this through. Cosine is a positive number more than a half. If you don't get this, just use your calculator. Cosine is a positive number more than a half. So if this is a number more than a half, 2 times it will be a number more than 1. 1 minus that number bigger than 1 will be negative. By the way, I know this is really tricky, and you have a lot to learn from this example. I know that it has to change to positive because this was a critical number for that 1 minus 2 cos x. But ultimately, here's what you can do. Put in for y. I'm going to get a different calculator going. No, I don't need to. put in for y 1 minus 2 cos x. Set up your table so that you can enter values of x, so you change independent to ask. Go to your table. Pi over 3 is pretty darn close to 1 point something. Pi is 3.14. 5 pi over 3 is pretty darn close to 5. And this is 6.2. So I'm going to put in a number in this interval, in my table. I'm going to put in 0.3. I get a negative. So I put a negative in that position. I'm going to put in a number between 1 and 3.14 radians, so 2 radians would work, and I get a positive. Now I'm going to put in a number between pi and 5 pi over 3. Pi is about 3, right? We're not splitting the atom here. 5 pi over 3 is about 5. 4 would be in there. And we're just about done, because we're not going to actually do much more here. 4 is still positive, and I could have told you it's still going to be positive because this point and this point are the critical points for that factor. It's where the sign changes. If you do it again, you'll get negative. So what I would say to you is completing this chart is done, I don't know, by hook or by crook. I don't care how you do it. You got to figure out how to populate that chart with positives and negatives. What does that mean? It means that dy dx is negative times negative is positive, negative times positive is negative, then positive, then negative. So there is at pi over 3 a max. I don't care what the y coordinate is. That is not the point of this question. Okay? Maybe I should put in here as well, the reason it's a max is because y is increasing, then decreasing, then increasing, then decreasing. This would be a min at pi. This would be a max at 5 pi over 3. Well, let's check it out. Was it cos x plus sine squared or minus sine squared? Plus? Right? All right, there it is. Rather than going into my calculate menu and finding max mins, all I'm going to do is go trace and enter pi over 3. And you can see that it lands at the max. You could confirm that that is a maximum by going to your calculate menu. If I go trace pi, there's the min. If I go trace 5 pi over 3, there's the max. By the way, there is also a minimum at 0 and a minimum at 2 pi, but that's not important for what we're learning today. It's because the function is increasing everywhere after 0, so there must be a minimum at 0. And it's decreasing everywhere before 0, so there must be a minimum, or before 2 pi, so there must be a minimum at 2 pi. The only thing I'm really assigning today for practice is 3 and 4. Let's just see. Number 3 is this. If you want to pick one of these to try to find an equation of a tangent line. And number 4 is trying to find max mins using this. I will tell you right now, I will not on this exam be testing you on that question that we just did. I don't mean that specific one. On doing a first derivative chart with a trig function. I can still ask you about it. I could show you somebody else's first derivative chart of a trig function and ask you to tell me about what's going on. But ultimately, today's lesson is about finding equations of tangent lines. So I would focus on number 3. And before anybody asks, none of today's stuff is on your little quiz tomorrow. Quiz tomorrow is about differentiating sine and cosine functions. Okay, Liam.
For the quiz tomorrow, do we have to worry about simplifying with identities?
Yes. The question is, do you have to worry about simplifying with identities? And I'm going to say yes, because the questions, if they do require simplification, will not require you to go down some really muddy path to do so. It might be something where once you differentiate, if you factor a sine out, you see you're left with 1 because it's sine squared plus cos squared or something like that. I would also expect you, everybody, that if you ever saw sine x over cos x, that you would write tangent of x, right? So the focus, and because it's a short period of time tomorrow as well, for the quiz. The focus is not on identities, but there might be a little bit of work there. All right, get to work on that stuff, please. You can practice to get ready for your quiz for tomorrow. Nicole, Demi, and Zach, I've been in contact with Ms. Townsend, and I think she has to get back to me yet, but you'll probably be doing this during your directed learning, I think. But she will be in contact with you, and if it's the case that you don't have quite as much time as us, then I will be forwarding a slightly shorter quiz to her. Okay? So everybody get started on that. What's going on here? What? Yeah. Okay, yeah. Okay, so get to work. I just have to do a couple of quick things at my computer, and then I'll take a quick walk around the room.